Well, to save time, let's not do the mechanism here. Let's just draw the product. We should also be able to do these with just the product and not doing the whole mechanism. So let's just write the product of this reaction. And this should be very similar to what we were just doing. Good. Now we're going to have to decide with the nitrogen nucleophile, what category are we going to be in here?
3.
Category 3. That's right. How do we know that this can do category 3?
Because it's a primary amine.
Right. Now, technically, I don't know if we would call this primary because it's not attached to any carbon chains. So I don't know whether technically it would be called a primary. But the key is it has 2 protons. The nucleophilic nitrogen has here 2 protons, so it can deprotonate twice, so it can attack twice. Technically, we probably wouldn't call this primary because it's not attached to any carbon chains. But it behaves the same as a primary nitrogen because it's got the 2. So what really matters is not the primary, secondary, or tertiary. What matters is how many protons is the nitrogen attached to. If the nitrogen is only attached to 1 proton, it can only attack once, and it would have to be category 4. But if the nitrogen is attached to 2 protons, it can attack and deprotonate twice, and then it would be category 3. So to draw the product here, again, maybe it's helpful to keep asterisking the carbonyl carbon. Who's the nucleophile that's going to be attacking twice? Well, one of these nitrogens. Doesn't matter which one you use because they're symmetric. And the important thing to realize is that since this nitrogen is attacking twice, it has to deprotonate twice. So it should not have any protons left. That's one of the mistakes I mentioned that I make a lot, putting the wrong number of protons on nitrogens. If you weren't sure about that, you could go through the whole mechanism and you could see how it deprotonates twice. But we should also be able to see this is going to lose 2 protons even without doing the mechanisms. If you attack once, you have to deprotonate once to stay neutral. And if you're going to attack twice, you have to deprotonate twice to stay neutral. Of course, this nitrogen is not attacking, so it doesn't lose any protons. This nitrogen is just along for the ride. This is what we called the R group before. It's not going to get changed at all. So here's our product as our normal category 3 type reaction. Now, what's the name of this type of compound over here? Remember, it's probably best not to call this a primary amine. There's a special name for this, which is hydrazine. That's on page 2 of the handout. I listed the names for a bunch of these common nitrogen-containing compounds. This is hydrazine. And there's a similar name for what we get over here. That's also in the handout. This is called hydrazone.
Makes sense.
Just a variation on hydrazine. Sorry. You can see here on page 2, on the product, we get an imine from a primary amine. We get a hydrazone from a hydrazine. Well, from this hydrazine, we got the hydrazone. All right, so that's just review so far. Now the next step, let me give myself some more space. Now we need to memorize what happens with these reagents.
Okay.
A hydrazone plus aqueous basic conditions and heat. This is the Wolff-Kishner. These are fairly strong conditions, and what this turns out to do is it just completely blasts off the nitrogen. It just completely blasts off the nitrogen and just leaves us with this. Basically, it's replacing the nitrogen with 2 hydrogens. We don't necessarily have to draw the hydrogens because we can just treat them like hidden hydrogens. So this carbon used to have 2 bonds to this nitrogen. That's been blasted off and replaced with 2 hydrogens. The nitrogen, by the way, leaves as nitrogen gas. So this is certainly not reversible because the nitrogen gas is just going to bubble out of solution.
Oh, yeah, I remember
So we don't need to worry about it going backwards because the nitrogen gas is gone. It just bubbled out. Well, this is a very useful type of reaction because what do we call this? When would we use this in a synthesis? What do we call this? This is what we call defunctionalization. where you completely remove a functional group, and instead of replacing the functional group with another functional group, you replace it with no functional groups, just with hydrogens. If you replace a functional group just with hydrogens, that's defunctionalization. This is very useful in synthesis because we don't have very many ways to completely replace a functional group just with some hydrogens. I think last time we did we saw another way to defunctionalize using sulfur, thioacetals, so you might want to review that. So how do you, I think we saw how we can make a thioacetal and then treat that with Raney nickel. Yeah, so you might review that. The thioacetal plus Raney nickel, that also is a way to defunctionalize. So how would you know which one to use? Well, the thioacetal plus Raney nickel, that would be useful under neutral conditions. But this is basic conditions. So if for some reason you want to avoid basic conditions, you could use the thioacetal plus Raney nickel. On the other hand, if you don't mind using basic conditions, you could use this reaction. This is, I think, used much more often than that sulfur reaction. Some courses don't even cover the sulfur reaction, but this is a very important reaction that you're pretty sure to see on the exam. So this is an important reaction to know. And like I said, this is called Wolff-Kishner. Wolff-Kishner. I think Wolff has two F's, something like this. Wolff-Kishner. I'm not sure whether just the last step is called Wolff-Kishner or also when we made the hydrazone in the first place, because these are kind of a combined thing. First we need to make the hydrazone and then we use the basic reaction. So this whole process of defunctionalizing is called the Wolff-Kishner reaction over here. Later on you're going to learn another reaction that allows you to defunctionalize under acidic conditions, and then you'll have ways to do it under acidic, basic, and neutral conditions. Later you'll see the Clemmensen reaction, which allows you to defunctionalize under acidic conditions if that's what you want. So this is a good way to defunctionalize under basic conditions, a base, water, and heat. Mechanism, you might be tested on the mechanism for this, but it's probably not the best use of our time. It's in the second language book, and if your instructor wants you to know it, it's in your lecture notes. So you can probably go through the mechanism for this step on your own. Unless you're actually asked for the mechanism, you should just write the product here. The mechanism is kind of complicated. It doesn't leave you too much knowledge. So just blast away this functional group. You're pretty sure to see that on the test. That make any sense? Okay. So. So let's write the product from this. Let's try writing the product from this reaction. We won't bother going through the mechanism, and actually you should be able to just go straight to the final product. If you want, you can just go straight to the final product here, or you can write the intermediate. There'll be an intermediate from step one and then a final product, but if you want, you can just go straight to the final product. Great. So one of you wrote down the intermediate and one didn't. That's fine. If you wanted to, you could just go straight from here to here. Remember, the whole purpose of this whole Wolff-Kishner setup is just to blast away the functional group and just replace it with two hydrogens, which we don't even need to draw if you don't want to. This was the intermediate. The first step we know is reversible, but obviously the second step is not reversible. Once the functional group is gone, we can't just go into reverse. So this is an irreversible way to get rid of the functional group. All right, so it's good to be able to just go straight from the starting materials to this product. So that's one of the usefulnesses of these nitrogen nucleophiles. They're the first step of this Wolff-Kishner. You start by using hydrazine to make a hydrazone, and then you use the water in basic conditions. Okay?